like to thank the previous speaker for an excellent introduction to what you can do with topic models. I'll present some of the work that we have been doing with topic models, and this is joint work with Linköping University and KTH. All right, so LDA also is one inference procedure to do topic modeling. It's short. It's usually shortened by LDA, and some people are confused because they think it's linear discriminant analysis. That's not the case here. So it's a unsupervised, hierarchical Bayesian clustering machine learning method. And as you saw in the previous talk, it lets you find topics in large document collections. And I'll probably use the word corpus or corpora, so just so you know what it is, that's just a big document collection. And in machine learning, it can sometimes be used as an alternative to TF-IDF to model unstructured text. And TF-IDF is just basically counting the word frequencies in a document collection. And this model is extremely popular. It was published in 2003, and it has like 20,000 Google citations, which is a lot if you're in academia. And there are many, many extensions that build on LDA. Okay, so what is the bearing idea here? Well, the bearing idea is that one document contains a mixture of several topics. So in this document, we've colored the topic. So we have a pink topic, we have a yellow topic, and we have a blue topic. In reality, each of the words have one color, but in this particular view, we've only colored some of them. So what is a topic then? Well, a topic is a probability distribution over words. You can see that on the left-hand side here. So the yellow topic has high probabilities for the words gene, DNA, and etc., while the pink topic has high probabilities for life, etc. So all the words are available in all of the topics, but the probabilities of the words differ in the different topics. On the right-hand side, you can see the topic distribution over one document. So here you see this mixture of topics for one particular document. So we can see that the yellow topic has a high probability for this document. The pink topic has a bit lower probability, and the blue topic has the lowest probability for this particular document. And every document has one of their own mixture distributions. For each of the words in the text, there is a topic indicator. So we can see this round discs, the purple disc and the yellow disc. Those are the topic indicators for each of the words. And these topic indicators are typically denoted Z in the math and in the literature. And those Z's you have to remember because they're one of the bearing components which we do calculations on. Okay, so of course in the real world we don't have these topic distributions, and we don't have the word distributions for the different topics. We have the documents, right? So what the LDA does for you is go from this document collection to these probability distributions, and then you can use them in applications that you heard in the previous talk. And these probability distributions are usually called latent variables. Latent Dirichlet Allocation, also called hidden variables. All right, so here's the model for the LDA, and this is a so-called graphical model. And in this graphical model, you can see this rectangle with a D, and that represents the documents in the collection. You also have, within the D, you have the N words for each document, and these are called plates. You also have a separate plate for the topics, and the topics are typically denoted K. So we have to manually select how many topics we want to see in this document collection. So we select K manually. This graphical model is a great way to kind of visualize the model, and then you can take this graphical model and fairly straightforward translate it into a probability expression, which is see down in the farthest down in this picture. Okay, so what do you get out from the model? Well, you get these topics, which are kind of themes in text. So here we've run LDA on documents from the Mozilla corpus, and the Mozilla corpus are bug reports for Mozilla Firefox browser. And we can see that this topic model has found these 4 topics. These are a subset of all the topics. I've selected these ones. And we can see topic 11, for instance, is kind of networking topic on a bit of a higher level. We can see topic 13. That topic obviously deals with printing and printers and so on. Topic 27 deals with layout issues and putting things on the screen, like background, color, border, etc. And then we have topic 28, which is again a networking topic, but on a bit lower level. Right? So this is what the model has given us. This is the output of the model. So we've run all these documents through the model, and this is what we get out. So now what can we do with this output? Well, we can go back then to the documents and look at individual documents and look at the topic distribution for one particular document. And that was denoted with on the right-hand side with this topic mixture on the graph previously. So here we see that document 255 has basically just talks about one single topic. It's a very focused document, while document 547, it's a bit more mixed, and document 1333, and these documents here are bug reports, right? And bug report 1333, it really doesn't know what it's talking about. It's talking about everything, basically. So that's something you can do with it. You can also plot documents based on their topic distributions. And here we can see there are clear clusterings in this plot, right, over these documents, which is pretty interesting because I've colored them based on the category of the bug report. And we can see there are clusters with a mixture of bug report categories, which can in turn lead to interesting leads when you want to study all these bug reports on a higher level in an organization. Okay, so how do you do inference in this model? So inference is calculating these probability distributions. Well, there are many ways to do inference in LDA. There's variational inference, expectation maximization, and probably the most common, perhaps, is a technique called Markov chain Monte Carlo. And we will focus on Markov chain Monte Carlo, and specifically the main focus is one that uses Gibbs sampling. So what's the problem with doing inference in this model? Well, we have almost infinite number of documents, right? Say they want to do topic modeling on the internet, right? We have a lot of documents, and this gives us even more Z's, those topic indicators that we talked about. And those are the ones that we have really, really many over. So we want to parallelize this inference procedure to do it fast. And since the heavy calculation is on these Z's, because we have a lot of them, we want to parallelize over documents. So that's the ideal approach. Okay. So there are a couple of main approaches for this. And the original core one was the method by Griffith and Stavers, and it's called the collapsed Gibbs sampler. The most dominant method nowadays is probably the isLDA method, which builds on this collapsed sampler. There is a sampler from Yuan et al., which is called LightLDA, which improves on the computational complexity of the original Gibbs sampler. So the original Gibbs sampler has a computational complexity per document that is n times k, which means for every word in the document, you have to sample k topics, right? And if you have a lot of documents, this turns into really high complexity very fast. So what Johan and I managed to do is actually squeeze this complexity down to order n, i.e. one draw per word. And that's actually, they use a Metropolis Hastings method. What we have done is a method called partially collapsed LDA, which also uses Gibbs sampling, but we improve on the original collapsed Gibbs sampler with this a bit complicated expression. But basically, it's you get the minimum complexity over topics and topics per word. So we can squeeze this complexity a bit smaller than the original one, but it's actually not as good as order n. But the interesting part is that even though our computational complexity is worse in this sense, it turns out to actually be more efficient anyway. And we believe that this depends on the actual sampling efficiency of the Gibbs sampler versus the Markov chain Monte Carlo approach. Okay, so here's the collapsed Gibbs sampler. What it does, it collapses away, it removes some of the random variables in this model, and this makes it actually impossible to parallelize the method correctly, because you get a dependence relation on each of the draws of the Z. You get a dependence relation, so you have to know the state of all the other Z's in the whole corpus to draw this particular Z. Okay, so the collapse sampler starts with this expression we saw on top here. It's the one you saw on the bottom of with the graphical model. It does a lot of math and ends up with this expression in the bottom. And this expression actually contains this dependence between these Z's that we cannot get away from. Okay, so this dominant approach called ADLDA, what does it do? Well, it is the dominant approach, and there's a lot of derivatives of ADLDA, and they all build on the same idea. We ignore the fact that we cannot parallelize over this Z, and we do it anyway. And this actually works quite well, but in fact, it's not the correct LDA sampler because of this dependence relation that we have. So what do we do with our sampler then? Well, we start with the same expression, but we only go halfway. So it's partially collapsed, and we save some of these random variables. And when we save these random variables, the documents can actually mathematically correctly be sampled independently. So we can completely parallelize over documents and still have the correct model. This is also very nice because we can exploit so-called job stealing in this parallelization, which means that if we have one large document and a small one, and a small thread finishes fast, it can steal documents from the other threads. And this turns out to be a real efficiency. This also works quite well, and it is in fact the correct LDA sampler. So why do you care about that? Well, it's important for downstream methods. If you build sampler on this approach, you really want to know that it's the correct sampler, because there's actually no error bound on the ADLDA. And why would you use an approximation when you can use a correct version and there is no decrease in efficiency? So how do we recognize a correct sampler? Well, a correct sampler will reach the same log likelihood independent on the number of cores. And here the different colors indicate the number of cores. And you can see for our partially collapsed sampler, we reach the same log likelihood independent on the number of cores. But if we look at the ADLDA, it's pretty clear that the log likelihood actually depends on how many cores you want. So what happens now? We've scaled this to 8 cores in this picture. What happens when we scale it to 1,000 cores? Well, we don't know. Okay? With our model, you don't have to care because it is correct. And we can actually do this without sacrificing speed or efficiency. So here you can see, well, maybe you can't see, it's a bit small. Oh, you can see. So the purple line here is actually our sampler, and the light blue is the ADLDA sampler. And closer to the left-hand side, getting to the top is better. All right, so that's all fine and dandy. Now, what can we do with this? Well, at Ericsson, we have this huge development environment, and we have large and complex products, and our support organization kind of reflects this fact. Right? So typically how fault localization and bug routing is done in a manual fashion, and this is not just Ericsson, just in general in large companies, that you have a customer detects some problem, the customer calls our support hands this off to further second line support, which in turn hands it off to design perhaps, and the design needs to figure out, well, where is this bug located? And then the design teams do a correction, we re-verify the product and re-deliver it out to the customer. And so the real challenge here then is when this new bug report comes in, we have two problems. We have to find a team to deal with this bug report, and we have to locate where in the software architecture this bug report is located. And this is kind of two sides to the same problem in a sense. Okay, so what do? Well, we measure this in routing time. We want to minimize the time it takes to hand it off to a team and find this bug report. And we quantify how well we do by prediction accuracy on this problem. So finding the correct team or component on the first try is a hit, otherwise it's a miss. And this unfortunately takes quite a lot of time. And why is that? Well, this bug routing is typically done by humans. And humans, they do other things than just routing bug reports. We do some diagrams sometimes, and we go to Fika and so on. So what we would like to do is add a machine learning component in the beginning here and say, well, now we get in a bug report. Can you please have a look at this and do this routing and find where the fault is located automatically? Now, what we want out of a model here is to say, and it was mentioned previously today, we want to know the uncertainty in this prediction. How certain is the machine learning task on this? So if it's very certain, we can accept this automatic routing and let the machine do it. But if the machine is uncertain in the prediction, we'd rather hand it over to a human and let the human do it. So we've studied this problem before, and we've used an ensemble technique called stack generalization, also known as stacking. And stacking gives a very good accuracy, but in terms of interpretation, it's a bit of a black box. So it's hard to understand what happens, and it's hard to get a good uncertainty measure from this stacking approach. So can we find alternatives then with good performance but an interpretable output that we can understand what the machine is doing? And there are requirements because this model needs to handle both numerical data and nominal data like classes, and this unstructured text, because in the bug reports there is a section observation text which the customer has kind of observed the problem and described it in prose. Now you might think, well, maybe we could use natural language processing for this. It's been mentioned here today. Well, the problem is it's not Shakespeare writing these texts, right? So there's a lot of strange input in this unstructured text, and these natural language parsers have a problem dealing with this because it's template code, there's machine generated logs and so on. So it's a bit problematic. So what we've done then is create a Bayesian classifier using LDA and another technique. And the nice aspect with this Bayesian model is that it actually gives us a probability distribution on all of the parameters in the model, which is very, very nice. And this is, of course, if you use a truly fully Bayesian model. You can do point estimates even with Bayesian models, but here we're talking about this full probability distribution that we're interested in. So we combine LDA with a Bayesian classification technique called diagonal orthogonal probits. And the nice thing with that is that it's a linear classifier, and that has advantages and disadvantages. The advantage is that it's easy to understand what it does. The disadvantage is that it hasn't got the flexibility in like a support vector machine, for instance, to adapt to very non-linear problems. The deep learning models also does this. All right. So what do we get if we combine DO with LDA? Well, we get DOLDA, which is a linear classification model, and it can handle unstructured text flows. So what do we want to do then? Well, we want to go from a bug report to a probability distribution over these classes, right? And the classes here are either the design teams or the components in the system. Again, we want to have some nominal inputs, like which customer, which site was it, which country, and we have this observation text. And numerical data, typically machine learning models have no problems with at all, but this text can be a problem. And typically we represent this unstructured text with this TF-IDF that I mentioned previously, which is basically counting the frequencies. The problem with that is there's no clear semantics in the TF-IDF, but LDA gives us these mappings with the topics in the documents. Okay, so the nice thing then with our DOLDA model is we actually get a very rich output. So here we're looking at one of the classes in the Mozilla corpus, and we're looking at the particular class core networking, the core networking component in the Mozilla Firefox browser. And here we can see that our model gives us these weights, the beta coefficients for each of the different topics, which are topics that are highly influential for this core networking component will have positive coefficients, and ones that are doesn't impact this component will have negative components. So we can see topic 11 and topic 28 have positive coefficients, and topic 27 has a negative coefficient on this core networking class. Well, what does that mean then? Well, we can look then at topic 11 and topic 28, and we see that these are typically networking topics, right? Which makes sense. If the bug report talks about networking topics, then it's probably located in the core networking component. While topic 27, which had negative coefficients, talks about layout and colors and those kind of things, which also kind of makes sense. Why would you send that bug report to the network? Okay. Another advantage with our model then is that we get this uncertainty measure. The model can tell us, well, I'm 80% certain that my prediction is correct, and we can then give a kind of an explanation to the engineers that looks at this prediction later on. And the model can kind of say, well, I'm highly confident in this prediction, that it's the core networking, and that's because this bug report talks about networking topics and doesn't talk about layout. So we get a kind of an explanation why the model does a particular prediction. In the contrary case, where we have a lot of uncertainty, the model can just say, well, I don't know what's going on here. It's just a jumble of topics. This guy doesn't know what he's talking about. Some human has to do it. And this uncertainty measure actually gives us a way to trade prediction accuracy versus automation level. And we can say as an organization, well, let's say that we accept a prediction accuracy of 60%. Well, that in turn will lead to that we need a certainty in the model of 80%. Well, if the model has to be 80% certain for us to accept it, we actually only get a 50% automation level, because the other bug reports will have to be handed off to you. And then we can do this trade-off in the organization. Okay, so let's look at some prediction accuracy. So here we've compared our DOLDA model with this stacking approach that I mentioned earlier. And it's actually we've run it here on 4 different data sets, Mozilla, Eclipse, GNOME, and some telecom data sets. And the model actually, ironically, does better on all the data sets except for the telecom data sets, where the stacking does that best. We think that this might have to do with, we've run this stacking for a long, long time on our data, so it's kind of, we believe it's a bit biased towards that data. The figures in parentheses here is when we tell the model to be absolutely certain to accept a prediction. And then we actually get really, really good figures. Well, we get 93% on the telecom data set. But here it means that we only get automation level on like 10% of the bucket loops. But there we're pretty certain that the model is correct. Okay, so what's the conclusions? Well, we can do fast, efficient, and parallel inference in the LDA model without sacrificing correctness or efficiency or anything. So it's a correct model that is fast and works. Didn't talk so much about the polyarn model, but in the polyarn model, which we also developed, we can get even more efficiency by exploiting sparsity in both topics per document and topics per word. So actually the polyarn model is the one you want to use because that one's even more efficient. We can combine LDA with this Bayesian classifier and get uncertainty in all the parameter estimates, including the predictions. And the DOLDA model gives a rich interpretable model with good performance, and you can use it very flexible in your organization. And we can trade this degree of automation versus accuracy. And for future work, we'd like to look at classification trees and do inference in these more tree-like structures. Like for our architecture is typically a hierarchical where we have like nodes, and the nodes have subsystems, and the subsystems have components. So do this inference in this whole full model would be super, super interesting. Okay, and that concludes my talk.